The right-hand system for cross product is based on this right-hand system idea. So if the X is the thumb, the index finger, the Y, then the Z-axis is the direction that the middle finger points. I don't really find that convenient. I like the corkscrew idea better. If I put the fingers of my hand, this is the way I think of it. I put the fingers of my hand in the direction of X and move them or fold them so that X moves towards Y, then my thumb will naturally be pointing in the direction of Z. So if you rotate the X-axis toward the Y-axis, so I fold the fingers of my right hand, of course, right hand, in towards the palm of my hand. Okay, so my fingers are in the direction of X and it's being folded towards the direction of Y, rotating in. Then my thumb points in the direction of Z. The other way to think of it is if you're taking something and you're tightening it with your hand and you're turning it, a certain way at least, your thumb points in the direction that we're talking about. So for cross product, and here it is, by definition, the magnitude of the cross product, A cross B, so not A dot B anymore, it's cross product, A cross B, we say, is mag A times mag B times the sine of the angle, theta, where theta is the angle between them when they're placed tail to tail. Not theta, sorry, alpha. Why alpha, not theta? Good question. Don't know an answer. A cross B is perpendicular. So this is a vector quantity. So notice in part A, it was the magnitude. A cross B itself is a vector quantity. And A and B lie in a flat plane. Then X will be perpendicular. Sorry, the cross product will be perpendicular to the plane containing A and B. So imagine, put two pencils, non-collinear pencils on your desk. Call one X and one Y. Put the erasers of your pencils together. So that's the tails together. If you rotate the X pencil towards the Y pencil, then the direction would be would follow, right? So if you're rotating the X towards the Y counterclockwise on your desk, then the cross product would be out of your desk. And if it's the reverse, then it's into your desk. It's hard to visualize maybe. Oh, here we go. Another set of pictures. So, if A and B are on your desk and you rotate counterclockwise from A to B and coming out of your desk, if it was the other way around, A here and B here, and you rotated A towards B, okay, then A cross B would be down or into the desk, right? A cross B would be down or into the desk. That's the idea here. Okay. Specific cases, if A and B are parallel, then alpha is either 0 or 180 degrees. So it's either parallel in the same direction or parallel in the opposite direction, right? 180 degrees opposite direction. The sine of 0 and 180 is 0, so the cross product would be the 0 vector. If they are perpendicular, if alpha is 90, then the minimum magnitude, the maximum magnitude would occur where it's the magnitude of A times the magnitude of B. If A and B are the same vector, then alpha is 0 and A cross A is 0. The magnitude of two vectors are 2 and 3, respectively. The angle between them is 60 degrees. Find the magnitude of the cross product. So we start off with saying we're going to find the magnitude of the cross product, and by definition, this is the magnitude of the cross product. So we have 2, 3, and notice if they were negative in some way, well, magnitudes are always positive, so I guess it doesn't matter. Sine of 60, and of course the angle is always between 0 and 180, so think about that. Yeah. Anyways, there we go. And the answer to this is 3 root 3, right? Sine of 60 is root 3 over 2. So the answer to this is 3 root 3. Example, some specific cases. So a vector crossed with itself has a alpha of 0. So all of these will be 0. And if you think about it, yes, the k vector for sure. I crossed with k gives you, j crossed with k gives you the I vector, and k crossed with I gives you the j vector. Yes, good. Now we're right away going from geometric to algebraic. And so we have three-dimensional algebraic. And here we go. A has components AX, AY, and AZ. B has BX, BY, and BZ. So, they're the scalar components, or, the coefficient of I, J, and K. And, you look at this. This is how you calculate it. You get a vector with, X, Y, and Z components, or I, J, Ks. And this is actually determinants. That's what this means. These single lines, they look like absolute value lines. Well, this is another use of absolute value lines. Absolute value lines can mean absolute value. They can mean magnitude. In this case, they mean determinant. And we're not going to learn determinants. It's not part of the course, and we won't spend time on it. When I was taught how to do cross product, I was taught using determinants, but that was part of that course back in the old grade 13. What we do instead is talk about this. So we're going to practice this using actual numeric examples and cases, but this is the method of calculating cross product that we use. And the idea is that you list the components of the A vector and the B vector as shown here. So you go AX, AY, AZ, AX, AY, the same. You could list AZ again, but it doesn't matter. The very first column of that's ignored, and then you multiply top left, so top left to bottom right. So we do AY times BZ, okay, minus bottom left to top right. So minus bottom left to top right. So that's AZ BY. And I just put the A term first. Now, if you look at that, AYBZ minus AZBY, and you look at the part above there, AYBZ minus AZBY, that's exactly what you have. Okay, now that's the X component of the result of cross product. So, if you think about it, this one here, top left, bottom right. So AZBX minus the other diagonal, AXBZ, and you'll see if you look, AZBX, AXBZ, yep. And then finally, the Z component of the result of cross product, the same idea, top left, AX, bottom right, BY, minus top right, AY, bottom left, BX. And you can see that gives you this. And so instead of memorizing this complicated formula, we sort of do this algorithm where we list the components and go through it in a certain pattern. So let's practice that. By the way, because we're not in the classroom, I usually do a proof here. I have in my notes that I usually do, but you're going to get that. If you really want it, you can Google it up on YouTube and you'll see a proof. I'm sure there's different people providing proofs. All right, so let's go through and do this. So off to the side, we're going to do a bunch of work off to the side. So what you do is you list the X, Y, and Z components of the A vector. And then you list the X, Y, and Z components twice, just like for the A vector, but now for the B vector. Now you ignore the first, and this is the crisscross here. So it is -4 minus 0. Then the next crisscross is 0 minus 2. And then the last crisscross is right here, -1 minus 0. And so we get -4, -2, and -1. So A cross B is -4, -2, -1. Okay, so there we go. All right. You try the next one. When you're ready, go ahead and run the video again, but set up the next one and you go through the calculation for the cross product of A cross B for the next one. Okay, so if you're here, you're ready. So I'll just list the components: -1, 2, 0, -1, 2, and 0. 1, -2, -1, 1, -2, -1. We ignore the first. We multiply here, so it's -2. Multiply here, so it's -1. Multiply here, so it's 2 minus 2, or 0. So A cross B is -2, -1, and 0. All right. Check that out and then go on to C and pause the video, of course, and then start it up when you're ready. All right, so components of the A vector and then of the B vector. And then we ignore the first, crisscross here. So 3 minus +2 is 1. -2 times -2 is +4. Minus -3 is +7. +1 minus -2 is +3. So A cross B for part C is 1, 7, and 3. Okay. Example 2C. All right, we're almost done this maybe. Properties, anti-commutative. So A cross B is not equal to B cross A. They're opposite to each other's. Look at this. The scalar can be multiplied into either of the vectors or after crossing, so you can do it either way. Distributive property does work over vector addition. Distributing cross product over vector addition works. So if the cross product is 0, then either A or B is 0, or they are parallel. Crossing any vector with the 0 vector is 0, and crossing a vector with itself is 0. And here's a bedmass statement, if you'd like, for vector calculations. Dot and cross products have a higher priority in comparison to addition and subtraction operations. Okay. Use cross product properties to prove the following. Now there's 4 proofs here. We're only going to do A and C. B and D I've been skipping for a while. Even this one here is only kind of interesting. But anyways, let's start with the left side. So A minus B crossed with A plus B, and distributive property holds. So when we expand this out, we get A crossed with A plus A crossed with B minus B crossed with A minus B crossed with B. Now, any vector crossed with itself gives you 0. So that's 0. This is 0. And remember the anti-commutative property of cross product means that this, of course we're not changing that, but this is the same as this. So we have 2 A cross B which is the right side. And that's quite easily done. Okay, so 3A. 3B, nope. I'm not going to do that one, like I said. 3C. This is actually called the triple scalar product. This is actually super useful. Not the fact that all three are the same, but just being able to calculate the triple scalar product. So this is a good one to do. The triple scalar product is a method of showing the volume of a parallel pipehead, which we'll see in the next lesson, but also to see if three vectors are coplanar or not, if the volume is 0. So it's a useful thing. We'll start with the left side. A dotted with B cross C. Okay, so we'll use the definition. So it's A dotted with, what's B cross C? Well, we'll use the components, okay? So this is BY CZ minus BZ CY plus, that's the X component. And then the Y component is BZ CX minus BX CZ, and then the Z component is BX CY minus BY CX. And of course, vector A, we're going to dot it now. Vector A is AX, AY, AZ. So dotting means multiplying the X components. So that we multiply AX times BYCZ minus BZCY plus A sub Y times BZCX minus BXCZ plus AZ BX CY minus BYCX. Okay. Now the thing is, we're going to look for and factor out BX's and then BY's and BZ because we're trying to show that connection. So where are there BX's? Here's one and here's one, right? So BX, and of course we're distributing, right, as well. We're doing everything in one step, if you like. So we'll go with the positive first. So CYAZ, so that's from that second one, minus CZAY. And why am I doing it in that order? Well, I'm trying to connect to this, okay? Now, pause the video and try to do the same idea for BY. Where are there BYs, right? And go ahead and factor it out. When you've given it a try, go ahead and start it up. So here we go. So we have CZAX from that first one, and from here, minus CXAZ. And again, if you haven't gone ahead yet, stop the video and do the BZs. Okay. We'll start with this one right here. So it's CXAY, and then this one here, so minus CYAX. Okay, and we're going to finish it up in one step here. This is B vector dotted with C cross A. And so you would just have to do it again, but you would factor out the CX, CY, CZ to get the third one if you wanted. All right, that's it for example 3. We're not going to do D. In fact, we're not going to do D. Triple cross product. Tried to find a meaning for this, but I'm not sure. Maybe there is, and I just didn't look enough, but we're going to leave that one. Find a unit vector perpendicular to both A and B. So any vector that's a unit vector that's perpendicular to both. Well, to get the perpendicular vector, we can just find the cross product. So, and divide it by its own magnitude. And there we go. That's the unit vector. Dividing by that magnitude, we make it a unit vector. And by crossing it, we find something perpendicular. So I'll list the components of A, list the components of B. Ignore the first column. Crisscross is -1. Crisscross is 1, and crisscross is -1. So there we go. The magnitude of this, of course, is root of 3. So what we have is -1, 1, and -1 over the root of 3. We rationalize that. So negative root 3 over 3. Root 3 over 3. Negative root 3 over 3. There we go. And then final example, example 5. We'll go through this taking a little bit of time. I'm going to start off and then I'll ask you to pause and then finish it. Okay. So this is a vector plus, cross product. What's the result of the cross product? A scalar or a vector? A vector. So can we add two vectors? Sure, we get a vector. So the answer to this is that it's a vector. So the answer is either a scalar, vector, or meaningless. This means a vector dot product results in a scalar, a vector, or meaningless. Well, of course, it's a scalar. Can we add a vector and a scalar together? No, so meaningless. Get the idea? Go ahead and go through and then start the video again and watch a few more, and then you can check the rest. So this is vector minus vector. Cross products are vectors. Can we subtract vectors? Sure, we get a vector. So in the bracket, we have a scalar times a vector. Can we multiply? Yes, we get a vector. This is a scalar in that bracket. And the bracket means we have to do it first. Crossed with a vector. Nope, we can't cross. We can only cross vectors, so this is meaningless. Okay, pause and try a few more. This is scalar times a vector. The brackets touching imply regular multiplication. Can we multiply a scalar and a vector? Sure, we get a vector. Subtracting vectors gives us a vector. Crossing vectors gives us a vector. Can we multiply a vector by a vector? No. We can dot them, we can cross them. We can't do regular multiplication, so that's meaningless. Okay, here we go. This is the longer one. So scalar times a vector, that's going to be okay. Minus a vector. And this last bracket's another vector. Okay, scalar times a vector, that gives us a vector. Minus a vector cross a vector is a vector. A vector minus a vector is a vector. Okay, and the last one, what do we have? Scalar minus scalar times, so this is scalar, minus vector dotted with a vector, which is scalar minus scalar, which is scalar, which is, I guess, fine. All right, that's example 5. And that's the lesson for 7.6, the introduction to cross product.